For those who are here, we're going to talk about OpenShift and Kubernetes and Docker and containers. If you're not interested in any of that, this probably isn't the right talk for you. I'm Clayton Coleman, architect for OpenShift and container platforms at Red Hat. I'm also a contributor to both Kubernetes and Origin, so I've been involved in those communities for quite a while.
I'm Daniel Rieck. I run the cross-product integration team in systems design and engineering at Red Hat. All right. So, let's go. So, let's talk about complexity. Two slides. One is a picture internally from Red Hat. Another one is a picture I took of the internet, so it must be true. So a little bit of data from module counts. It's just the number of and growth of packages in some common repositories for popular languages. And what you see is that there is actually pretty strong growth in amount of content out there in these language repositories that developers pull from. And just for an order of magnitude to set kind of the baseline of what we're talking about, the green line at the bottom, that's a Fedora ecosystem. That's the RPMs available in Fedora Unstable, I think in 23. And the pink line above it is Debian Unstable, right? So we have about 30,000 packages in Fedora. There are about 40,000 packages in Debian. And there are 200,000 NPM modules out there.
Yeah, and you can see the exponential curve on this, right? Like that hasn't started to trail off or anything. That's just going up and to the right faster and faster.
And it's just a 10-month snapshot, right? So there's a lot of software out there that developers pull from. The other picture is just an application in managed IQ/cloud forms, visualized service dependencies. So what this tells you is that there are a lot of services, a lot of individual services that make up this thing they're monitoring there. And you can assume that each of these little things pulls from this ecosystem. And you have no idea what's running where. That is the complexity problem we're dealing with. And you probably saw this meme. I couldn't get the video to work in Chrome in the presentation. This meme about the late binding operation model patching things in production. So it's an old Buster Keaton movie, and he's on this train, and there is something in the way. He jumps off, picks this stuff up, gets run over, jumps back on the train, and then throws a big piece of wood to put another piece of wood out of the way. It's much better when you actually watch it. But the point is, what we do every day when we deal with this complexity, there's all this stuff and all these services, and when there's an issue like a glibc issue or left pad or any random issue, any bug, any broken dependency, any security issue, we go in the predominant operational model today, we go in and we try to update, have a sysadmin update this piece of code in the production environment.
Yeah, and the sysadmin is not even the person who wrote this application, right? So for the last 20 years, we've successfully, more or less, applied the pattern of somebody who doesn't write an application is responsible at their job level for keeping that application secure. And they don't know the implications of their change. But it works, and we've gotten this far with it.
Yeah. And so we do that at scale all the time on a component level, and I call it a late binding model because the stack doesn't come together until we install it. And what happens is we develop something, and because of this amount of complexity and the amount of change you're seeing with basically every other day a security errata or bug fix errata coming out on some component of the stack. And it's just for the RPMs, right? And everyone only uses RPMs in the application, right? No one uses anything other than RPMs in this room, right? Yeah, thought so. So, so you have these software stacks from somewhere, and you're getting all these errata, and you develop something, new or an update, and then you have a hotfix going out to your production system, so you test this, and between the time where your developer develops something and QE tests it, there's another update. So what you test is actually not exactly what you developed, right? And then after successful test, you take it into production. And somewhere in your software stack, from the Linux kernel over glibc, EAP to your Java stack and all the libraries you're pulling in, there probably was another bug fix or security fix between the time you tested and the time you wrote it out in production. So actually running in production is never what you actually tested. It's always slightly different because we expect that we can update this in production. And then when it's running in production and, you know, OpenSSL has another like big issue or something like that, we go out and we patch it in production. We think that's going to work because it's really urgent and nothing is going to break. And it's kind of working, right? And if it doesn't work, it's a big disaster. And this continues and continues and continues. And it's really like an eternal spiral of change we are in, where things never get consistent. There are big applications. If you look at the earlier picture I had with this dependency tree, you probably, in a large cluster, never have a consistent state of the cluster. Because once you're done patching on one end, the next patch already started rolling out across your systems. Yeah. Right? Keeps changing and changing. Oh, we pressed both. So I had a picture of a black hole there, which Clayton says doesn't look like a black hole. Yeah. But I got it from NASA, so it must be a black hole.
It's the 1980s black hole.
Black
holes are much cooler now.
I think it just ate the sun or something.
Yeah, whatever.
Anyhow, so what we basically constantly playing whack-a-mole, right? That's what our operational model is today. In a model where we are on the component level, we take individual packages, we roll them out, we take them through however sophisticated test and deployment cycle, and we update things on the component level.
Don't read this whole slide. There's
well, this is so you can download it and read it later. So, if we take back a step in history, you know, it's not always been that way. This is actually like the result of a lot of progress. You know, back in the day, you know, what we did is we compiled stuff in user local on each machine. You know, and we had a bunch of admins on each machine, big servers, terminals attached to it. It worked fairly well. The problem was that the behavior of the application and the stack depended on the state of the machine when you compiled in user local, and then use store tools like that to manage that, which didn't scale really well when you had more than a small number of machines. So when PC took over, when Linux took over, we switched to binary reproducible builds that have a binary distribution, like RPM. Right? And so you have defined dependencies, you roll out applications with the dependencies, and you can predict the behavior of the stack because that's encoded in the binary that has once built. The side effect of that was that we moved to a single instance, single version system. So you can only have one version and one instance of each software package in your stack. So we're moving to a monolithic software stack with this model. Yeah, you can add different ones, but then you have to rename the package, right? Anyone using Python 27, Python 30 is painfully aware of what that means, right? So we moved to a single, to a monolithic system, but with binary scalable redistribution. And then we added things like Kickstart and YAM and Satellite and scale-out management and CF engine and Puppet and Ansible. And
because we were starting to hit scale, right? Like this transition to RPM, you know, over the last 25 years or so, as we moved into this model, we started to go from there's a single system that runs, and there might be 2 or 3 of those systems, to 10 or 15. And then, you know, sometime in the mid-2000s, we introduced virtual machines. And virtual machines take the problem and then multiply it by 10, right? VM sprawl.
Yeah, well, VMs sound great because you get isolation. You can run different things, different versions at the same time. You know, move them on their own time. But you still have a monolithic system. You still use the same approach to manage it, and you have much more of those machines. Right? And so it's relatively heavyweight. It has a sprawl, and it doesn't solve the fundamental problems. Containers. And you were wondering why we're talking about, you know, basically old Unix servers and VMs, right? But the build-up is for containers. Containers are the logical next step. From a Red Hat point of view, containers basically are aggregate packages. Right? We take full software stacks, we package them with their user space dependencies, and we run them in a container, in a change root on steroids. So each service in your service architecture has its own binary runtime, doesn't need to merge the dependencies with other binary runtimes. So you get out of dependency hell with this.
Yeah, and we got Dan Walsh here, and Dan Walsh is famous for saying containers don't contain. But there is one thing that they contain extremely well, and that's dependency sprawl. Yeah. And that brings in new problems, but it moves the problem into a realm where it's controllable. So we talked about the admin, right, late binding. The admin ultimately is responsible for security, but the developer is responsible for the application. Right. And as these roles cross and merge, like one of the things we'll talk about in this session is how the tooling has to support the spectrum between them.
And containers move you into an early binding model where the developer packages the application with the binary dependencies, and you separate the binary dependencies of individual services from other services and from the underlying host. So you can run multiple versions at the same time. So let's take a step back. This is actually part of a bigger shift, right? We are faced with a big shift in paradigm. We have some macro trends. Macro trends. Macro trends. Everything is software, right? There's this quote from some I think BMW or Audi guy who said, the success of a car is not defined by car engineering anymore, it's defined by software engineering, right? That's where we are going. Everything is software. Actually the car is going to drive itself soon, right? So everything is software. And that means that business interests drive developers, which means that IT loses control. You lose the ability to standardize on a single monolithic environment. Open source now is the default. So everyone who's building application actually really pulls from these 600,000 aggregate modules across these languages. Most people move towards a cloud native behavior. Like the cloud really has one as the operational model right now. Doesn't mean everything runs in the cloud, but everyone has something run in the cloud at a point.
And I think it's important to notice too is that it's actually, we're starting to get to the point where when we say cloud, it doesn't really matter where the cloud is, it's what the capabilities of those clouds are, right? Like we're getting to the point where machines getting more complex. On a single laptop, I have more compute power available to me than most people had in their data centers 25 years ago, right? Some of those changes are also changing how we think about the cloud, is that cloud native means computing at this point.
And so as part of that, we're moving to aggregating services rather than monolithic applications. So this complexity of the dependency map grows and grows and grows. And you don't even know where these services are, where they run, what they run. There might be SaaS offerings, there might be software you run yourself, there might be part of a cloud environment or PaaS environment someone provides. There are tools and techniques that make this really possible, and it's DevOps and containers. Containers are a product and an enabler for this change. Containers create the application-centric runtime that allows you to make this flexibility happen.
And when we talk about, apparently I'm outside the range of the, I knew these things don't work. So when we talk about like, what is IT, the trends, this environment is, the whole point is the application, right? Like we build line of business applications and we support them and we have to update them and maintain them and they drive value. If a car is a unit of software, how do you deliver software to that car? How do you roll it out? How do you support the underlying infrastructure systems that control car repair maintenance? This web of interdependencies of software. So it all starts at the line of business, but everything else is in service to that application. And I think that's the real change that we're also talking about now with containers is, it's not that this is a new concept. It's that we're finally reaching the point of maturity in the infrastructure space where we stop talking about infrastructure for its own sake. So instead of saying, well, I'm just going to create tens of thousands of VMs that still have to be managed the same way, we actually have an opportunity now that we've reached a level of sophistication in our technology that we can build infrastructure software that is designed to run applications. The whole goal of the infrastructure is to run applications. And each of these layers, each of these roles, the infrastructure is actually the least important part. It's our cost model, it's our control plane, it's the compute and all that. But it really only exists to serve the developer. And the developer, in many cases, depending on how you might draw this, you might have IT on the inside or developers on IT on the inside. But I would say most people probably feel today like developers are pushing on IT. They're pushing it to go faster, to do more, to give up more control. We want to build more applications. In some cases, if the development organizations are outside of IT or not directly controlled by it, that pressure creates the wrong incentives in the organization. IT has a defensive mindset. And we really want to flip that. We want to say the point is to run applications. IT is just another facet of development. Each of these services is really there in the service of the application itself. So we're 15 minutes in. We should actually talk about what the strategy is. So
it wasn't the title.
I don't know what you guys are here for, but I'm here to talk about strategy. So The Red Hat container strategy ultimately is an application-centric strategy, and applications are at the bottom because that's what matters. Each of the layers on top are some aspect of the evolution of IT, the evolution of data center computing, how we think about the tools that enable this transformation. So more software, more applications running all the time, more automation, more tooling, more management is necessary.
So let's take a step back and look at the architecture you see there. From a Red Hat point of view, the stack for application-centric IT is pretty simple. We talk about infrastructure, application platform, and application. And you can map that to personas. Traditionally, you have the system operation, IT operation group, they own the infrastructure. No change here. Application operations, a group that kind of we see more and more evolving. They own the application platform. And we have development that owns what actually is the application. Now, the application operation group sometimes is part of development, then you probably have a DevOps environment. It sometimes is in systems operations, and that is more the traditional approach, but often enough we see it as a separate group now. This is kind of a service center or center of excellence that supports different development teams. And that model, these three layers are supported by two important ecosystems. One is for packaged services, which means reusable components that you don't touch, you just use. You know, the traditional binary software distribution. And by developer content, that is components you developers use to build applications.
And I think there's a really important note here as well is, we talked about the complexity of modules. We had a graph of how many different ways that you can find new JavaScript libraries to do something interesting. But on the packaged services side, there is also a revolution going on. Open source infrastructure components that are released and supported in the OpenShift. So it used to be just databases, right? Or actually, it didn't even used to be databases. You couldn't get an open source database that was any good. And now, increasingly, open source databases are a viable alternative. If you look at the cloud infrastructure, what people call giant microservices applications, tools like Zookeeper and Kafka and all of the big data frameworks, every single one of those is ultimately a successful open source project donated by a company to the commons. That software, in a sense, is helping enable that scale up to these large numbers of applications. Without that software, you wouldn't be able to do big data at scale. Nobody's selling a big data stack that isn't ultimately a variation of a support model for open source.
No. And so we'll talk a little bit more about that later, and we'll talk a bit more about developer tools and management tools, which obviously are very important. Developers need to build the applications, and then they still need to be operated.
And managers need to manage them. So if we're application-centric, what are the workloads that we care about? So historically, the last 5-6 years, we throw around words like platform. People say, OK, platform as a service. Well, platform as a service meant Heroku or kind of the early iterations of OpenShift. And that platform as a service was focused on simple scale-out types of applications, basically 12-factor applications or simple web apps. This is the easy stuff, right? This is the stuff that somebody can go throw together a demo and be like, look, it scales to 1,000. This is awesome. But ultimately, that's not actually the full workload, right? Like if you can kind of infer that there's just a bunch of dots there. There's a lot of other pieces to this. For instance, the first variant assumed that you had databases off the platform. It assumed that you had some sort of system of record where this data is going. And so the simple scale-out model is a great icebreaker, and it's something that, for more or less is a solved problem. You can get 17,000 different frameworks today that go do it in some variant. OpenShift, is ultimately about these services and enabling developers to build them. But this isn't enough, right? This is just the first step. And so the next workload really that matters, and this is a kind of a traditional workload that's been around for a very long time, which is the idea of a job or a batch workload. So processing systems, big data, any kind of simulation or other calculation workload, things that run for a specific period of time and then are done. And there's a ton of experience in this space, right? This isn't a new topic. For the last 20 years, people have been building grid workflows and high-performance compute. These are basically solved problems. But the challenge was that was always distinct, right? Those were always different from the scale-out application. And the goal really is to bring those together because at the end of the day, those are applications too. Those have development life cycles. Those have security issues. Those need to consume shared resources. If you have a big pool of physical hardware in your data center, you want to use that physical hardware.
And you need the services now, right? It's not that high performance computing is something in the niche in R&D anymore. It's a base for analytics for everything you're doing in the modern world, where machine learning and AI are the next big disruption.
And it's a great point that like the complement of these kinds of big data systems is you need something to report the results to somebody that can justify the budget that you're spending on all these computers, right? Like you need web services, you need APIs that allow you to go access that outside of your business. And so it's not enough just to support the simple scale out. It's not enough to support job and batch. This is actually an area that we at Red Hat are actually moving into very strongly in terms of enabling the core functions in products like Docker and OpenShift and Kubernetes. But we want to make an even bigger investment and enable the real expertise in this field, the people who have these grid engines and have built these policies out over many years, to bring those to the platform. The goal here is to make this a center of gravity for running applications, for enabling it, and it just happens to be in containers, but it really is just workload management. And again, all of the first order platforms, like the first platforms as a service said, well, we're not going to go deal with those stateful applications because that's really hard. And the change that we're really making, last year we announced OpenShift 3.0, and OpenShift 3.0 came out of the box with support for network attached storage. There's announcements going out this week. Hopefully they've been announced. Around storage and integration with OpenShift that make it easier to run storage. And ultimately, at the end of the goal, Red Hat's desire is to bring a platform that has access to stable storage. With that, you can start building the higher level capabilities on the platform. So you can bring legacy enterprise applications. You can bring the application server onto the platform and have some confidence that it's actually going to work.
So what we're saying is that we see mode 1, mode 2 really as a continuum. So our container strategy means that we will enable the convergence of 12-factor stateless applications, scientific computing, and mode 1 applications into the same platform, which implies things like scale out, pluggability for specialized schedulers, things like that. So it's an open ecosystem. It also means that we're going to have a standard service for high availability for stateful applications as part of the platform. So you don't need to install additional high availability cluster systems. The system itself will provide, the platform itself will provide the scale out and or high availability clustering for you.
And I think the observation is, again, this is about applications. There's lots of different types of applications, but they do have common needs. And we think we're actually at a point where what containers allow us to do is to make that final step to saying, we actually have a consistent environment to run applications, and we can build on top of that the higher level services that make those useful. So stable services and stateful applications really is one of the next big opportunities. And the next one really is a classic Red Hat focus area, which is high performance. I don't know if there's anybody else who's as good as optimizing up and down the stack when it comes to trying to make these kinds of applications work. But I mean, this focus is, we have grid, we have high performance compute, but ultimately big data is really just another variation of grid come around. And so high performance compute, these sorts of use cases, enabling the specialization that we have within Red Hat to make this work inside of containers, so that existing mode 1 applications or even bare metal applications that are working in a regular non-containerized environment, the disruption here is less about having to re-architect or to redesign how the applications work, but it's a packaging problem.
Right. But we can move your existing application into this environment. The environment can adjust to it. And if you look back at the big picture from the complexity slide at the beginning, it really comes down to like all of these services. Some of them are mode 1, some of them are mode 2, some of them might be analytics, some of them might depend on specific hardware enablement, specific NUMA or GPU capabilities. And the complexity affects them all. Right? The lifecycle changes, the complexity of code, the challenges of managing the dependency health affects them all. So a common application environment, or a common operational model is really beneficial for this environment if you can create such a platform that adjusts to the specific applications or even service within an application needs.
And we've filled out this grid here, and this is the idea that if you want to maximize your utilization on your own physical hardware, you need diverse workloads. That helps you, get up to those high percentage of utilization. But I think that raises the real question, which is, well, what if you don't want to own machines anymore? And that's where we're going now with the hybrid cloud.
So OpenShift, and that's the Red Hat container platform, the OpenShift container platform, basically provides a cluster is a computer scale-out platform that goes across the hybrid cloud. So in the earlier slide, I said we have the infrastructure. I described the infrastructure as being the individual hybrid cloud options from bare metal over enterprise virtualization, private cloud, public cloud. And what OpenShift brings you is a common containerized application runtime that runs across these different deployment models. So you can define your application once, right, consisting of mode 1, mode 2, or specific scalable or high-performance applications. And you can run it independent of what the underlying infrastructure is. Your application doesn't need to know. OpenShift does the mapping. And the application runtime, the runtime for the containerized application has a job to map your storage needs to the storage providers that come from the infrastructure. So it doesn't manage the storage providers, it maps them and manages your application storage needs.
And that mapping is really important, right? The idea of application-centric IT ultimately is that developers are targeting the capabilities they need. Each application has a set of needs, trying to find the standard patterns that apply across all these, and then make them work across the patterns. It doesn't prevent specialization. It doesn't prevent you from plugging in as necessary, but it does ensure that you have the broadest range of portability.
And this is all built on Red Hat Enterprise Linux and the Atomic host as an immutable infrastructure implementation of RHEL, so it is a different deployment model, which goes as far as saying you cannot install software on the host other than as a container. So we have concepts like super privileged containers for drivers, and we have then higher level concepts. So OpenShift itself can schedule containers or containerized application with privilege to even extend the host or the platform itself. So in itself, this is an extensible platform, and even the host capabilities can be extended with containers. So it's a very consistent model we are taking, not only for the applications, but even for the system itself. It's using the same capabilities to expand the system and the platform. And of course, it is end-to-end open source and standards-based.
So, and standardization is really important to us. Obviously, a foundation of portability is that you have some expectation that more than one vendor provides the capabilities that you need. And so as part of the Open Container Initiative, OCI, which is really focused on the container runtime level. So we have a number of people at Red Hat who've been involved in this from the very beginning. There's a ton of big companies who are interested in containers and Docker, and they want to take that next step to standardization. The goal of the OCI project, and they've made a lot of progress in this past year, to get to a 1.0 runtime spec, which is the container environment, and then from the Red Hat and the community perspective, extending that into the higher level platform. So extending that support into Kubernetes and OpenShift as we go, and also providing a common ground for vendors. So in a lot of cases, many of the companies on here are looking to participate and contribute. And this is the open source model in a number of ways, which is not just individuals coming together, but companies coming together with competing interests, but with the standard goal of being able to move these applications, because it's too important to let applications get locked up in a single format or a single vendor. And then on the flip side of that, with something which is a little bit newer, the Cloud Native Computing Foundation is something Red Hat is also a founding member of, which is an effort to work at maybe a higher level with a little bit less direct focus of trying to standardize the higher level concepts. And this is still very early in its process, but for instance, Kubernetes, the open source project, was contributed by Google to the Cloud Native Computing Foundation, and a number of other significant open source projects have been. And really this is to provide an incubation model that's similar to Apache in a lot of respects, that tries to help applications and customers and businesses make this transition. And being involved in that as well is really important to us to ensure we have a future for these technologies. So Ultimately, with applications, there's some level of this that has to do with security. So one of those top bullets on the container strategy was security, and that itself is a process. So there's a Daniel, your talk tomorrow on container security, which will contain all of the gory details, and it's a great talk. This is a really high-level view of it, which is the process, the change, the difference here with containers is before, in the late binding model, you made a bunch of decisions in a bunch of places that were different. So different physical machines might have different collections of things installed. It also meant that the results of a security scan on one machine didn't necessarily apply to the other because you had no way of ensuring that they had the same versions of the packages. With containers, one of the models that we're really trying to focus on is these small pieces of your application. As they move from these environments, the idea behind immutable infrastructure is they're the same. And because they're the same, you can do two things. You can say, if I know that I scan this up front, when it's running in production, I don't need to rescan the base content. All I need to scan is what's been changed. And so there's other capabilities that we'll talk about in the other talk. But ultimately, the idea of moving the software from a developer who puts all this together, the developer's doing some level of packaging, or the build systems or the application operations group doing some packaging, moving into production, and then using the results of scans in production to trigger processes earlier in the flow. That is what we call continuous integration in deployment, right? It is the same process. You don't want two processes for rolling out change into an environment. You want to find the process that's repeatable and iterable. And in order to make containers work, you have to do that, right? You have to build the container and then ship it. Well, if you want to apply a security patch, you need to build the container and ship it. And so the capabilities that we'll talk about over the next, the capabilities we'll talk about in OpenShift as we go over the next few years are about adding these capabilities. So OpenShift, I know this is really small here, but the idea of OpenShift is there's a number of services that are application specific. They're about the application lifecycle. One of the key parts of that is build and continuous integration. For developers, that's about iterative building, and there's a ton of platforms out there. OpenShift, over the next year or so, is going to integrate Jenkins in a deep way, but we also have a number of plug points for enabling other tools. The goal is to make the platform able to support continuous integration and deployment as effectively as possible, but to integrate the deeper levels of that process as well, because security is a part of the problem for a production environment. You need to have a process that can manage that.
Important aspect here is that OpenShift as a backplane, you can extend it within the end-to-end DevOps workflow. We can also extend it with tools that break out of the end-to-end platform and, for example, serve other architectures. For example, Red Hat Mobile does that. So you can take Red Hat Mobile running on OpenShift and serve mobile development. So it's both. It's an end-to-end DevOps platform, but it's also a backplane to enable other targets.
And I think that's a really important distinction as well, is that as a backplane, we know that customers have built and maintained systems that do many of the same things we're talking about here. And our goal is to enable a backplane that offers these capabilities, but that pluggability is key because we know that these are transition sorts of processes. This isn't a lift and shift. This is, over time, we want to enable the benefits of containers in an iterative model. And that means adapting to existing processes. Policy, this is probably pretty obvious, but if you have a runtime system that's managing hundreds and hundreds of hosts, ultimately that system is responsible for, are those hosts secure? Are they up to date? What are the policies that control who can run on that platform? What can they do? And so we think of, when we think of platform in general, the goal, as much as possible, is to ensure that there's enough hooks in the platform to take control, but then also to allow people to build sophisticated policy on top of the platform through platforms and management platforms, through third-party integrations to handle those work use cases.
So we won't be able to cover all of this in every level of depth, but for completeness, they're going to be separate. If you're going over to DevNation, you see a lot about our developer tools. So we have a whole set of initiatives around end-to-end developer tooling, around the Developer Studio, CDK, third-party integration. If you went to the keynotes yesterday, you saw a lot of that. Ansible has now container developer support. That's really interesting. So on one hand, we have the individual developer tools that enable you to use this end-to-end platform independent of what you're running on your laptop or what your company is running in the internal systems. It can plug in on the individual developer as well as higher level tools. And we are pushing that really hard. So it's a common platform. On the other hand, you have management, which obviously the operational side. Developers transition the individual application owner. Sometimes it gives them some more operational side in the DevOps environment, but ultimately the whole thing needs to be managed. Our management strategy is to integrate with CloudForms, which provides both the core container management, but also a single pane of glass across the hybrid cloud. So when you're running OpenShift as this abstraction layer across different deployment models, CloudForms actually can map to the different underlying infrastructures and give you a consistent view of that from the container to whatever the appropriate level is for virtualization or cloud instances.
And I think one important point that I bring up, if you guys do have a chance to check out the developer program work around Eclipse Che, one of the ideas around this is that a container is a really useful application packaging environment. But as a developer, when I want to have portable development environments, I may need many of those same tools. And so the real innovation that's happening in that space is being able to use containers as development environments in a useful way, not just as a toy that someone plays around on their machine, but to be able to treat that in OpenShift being able to run those containers as well. So the idea of the platform also being able to host development environments for end developers, but to be at each of the phases along the way for the applications as they mature.
Yeah. Now, on the management side, we are building on the complete Red Hat management stack, but we're also integrating third-party tools. It's pluggable on that level as well. So there is no single integration point there that would lock any other vendor out. And we're using Ansible a lot. Content management to satellite for the host layer, depending on where you're running, and then integration with the tools that the individual platforms use. And if you're an OpenStack user or you're in Amazon, you want the infrastructure level to use the native tools that you're used to in your production environment. So we'll integrate. Our strategy is to integrate with the best practice management for the infrastructure, so that we don't force the infrastructure ops people to use a tool that's foreign to them just to get the application. So when we say we want this abstraction layer, it means integrate even with the management tools of the underlying platform. Multi-container application. So taking another step back. So we talked about that a little bit, right? We separate runtimes, we get binary, we separate the dependency tree, we have independent runtimes for each application, and most applications will consist out of multiple services. So even most Mode 1 applications have 2 or 3 tiers, right? They usually are separated in the front end in a database and some business logic, right? So basically every application by default will be a multi-container application. Single container applications are an exception, and it's going forward, it's going to be less and less. Even on the desktop, I think what you'll see is more and more multi-container applications.
As a useful point, I mean, there's very few applications that run in anyone's IT shop that don't actually connect to LDAP. Right? LDAP is a service.